When we call a galaxy a vast city of stars, it's not just a poetic image, it's a surprisingly accurate way to capture how complex, diverse, and structured these enormous systems really are. To understand what that means, it helps to zoom in and build the idea piece by piece. Imagine you are floating far above the Milky Way, our home galaxy, far enough away that you can see it all at once. It would look like a great glowing disk with spiral arms gently curving out from a brighter central bulge. Those arms would shimmer with light like avenues seen from an airplane at night. But what looks like a continuous glow is actually the combined light of hundreds of billions of individual stars, each one as real as our sun. That's the first key idea. A galaxy isn't a single object like a star or a planet. It's an enormous collection of stars, all bound together by gravity. Our Milky Way alone is thought to contain somewhere between 100 and 400 billion stars. Some galaxies contain fewer, some far more. Giant elliptical galaxies may have over 1 trillion stars. When you look up at the night sky with your naked eye, you might see a few thousand stars at most. Multiply that by millions, and you start to approach the number of stars in a typical large galaxy. But just as a city is more than a crowd of people standing in a field, a galaxy is more than a random clump of stars. There is structure, organization, and dynamic motion. In a city, people live in neighborhoods, use roads, gather in business districts, visit parks and marketplaces. In a galaxy, stars gather in spiral arms, clusters, and bulges. They move in orbits around the galactic center. They live in different kinds of neighborhoods that shape their life stories. Take the Milky Way as our main example. Our solar system is located in one of its spiral arms, about 26.00 light years from the center, orbiting around the galaxy at roughly 220 kilometers per second. It takes our sun about 225 to 150 million years to complete one orbit around the galactic center, a period often called a cosmic year. That means that since the sun formed, it has only gone around the Milky Way a little over 20 times. Every star you see in the night sky is also orbiting the center of the galaxy, each on its own path, all responding to the combined gravitational pull of the galaxy's mass. The visible parts of a galaxy can be roughly divided into several components. There is the central bulge, a rounded, densely packed cluster of stars at the core. In spiral galaxies like ours, this bulge can range from a small, pea-like knot to a large, elongated bar shape. Surrounding the bulge is the disk, a flattened, rotating structure where spiral arms form. These spiral arms are not rigid objects, they are more like patterns, regions where gas, dust, and stars are slightly more concentrated, and where new stars tend to be born. Further out and above and below the disk, there is a diffuse, roughly spherical region called the halo, sparsely populated by older stars and globular clusters, ancient, densely packed groups of stars that formed in the early history of the galaxy. Galaxies also differ in shape and personality. Edwin Hubble, the astronomer whose name you may know from the Hubble Space Telescope, classified galaxies into several main types. Spiral galaxies, like the Milky Way and the Andromeda Galaxy, have beautiful, pinwheel-like arms. Elliptical galaxies are more like giant, smooth balls or ovals of stars, lacking clear structure or spiral patterns, often made of older, redder stars with little gas left to form new ones. Irregular galaxies have no obvious shape at all, often distorted by past collisions or interactions with other galaxies. Some galaxies have bars of stars cutting through their centers, with spiral arms extending from the ends of those bars. Our Milky Way is thought to be one of these barred spiral galaxies. Yet, what may be the strangest component of a galaxy is something we cannot see directly at all: dark matter. When astronomers measured how fast stars orbit within galaxies, they noticed something odd. The outer regions of galaxies were rotating too quickly to be held together by the gravity of the visible stars and gas alone. According to the laws of gravity, those stars should have flown off into space. The fact that they didn't meant there had to be additional mass, something invisible, to supply the extra gravitational pull. This invisible mass is what we call dark matter. We don't yet know what it is made of, but we see its effects everywhere. Galaxies seem to sit inside huge halos of dark matter, extending far beyond the visible stars and gas. In our city metaphor, if the shining disk of stars is the downtown area you can see at night, the dark matter halo is like an enormous, transparent infrastructure holding the whole city together. Without it, galaxies as we know them would not exist. Alongside dark matter, another remarkable feature of galaxies lies in their very centers. Many, perhaps most, large galaxies harbor a supermassive black hole at their core, millions to billions of times the mass of the Sun. In the center of the Milky Way, there is such a black hole, called Sagittarius Sagittarius A star, with about 4 million solar masses. Stars orbit this black hole just as planets orbit stars, following paths that reveal its presence through their astonishing speeds and tight curves. In some galaxies, matter falling toward these monstrous black holes creates intense radiation, making the galactic core shine as an active galactic nucleus or even as a quasar, one of the brightest objects in the universe. So, in this city, you have districts rich in young blue stars, like vibrant new neighborhoods where star formation is booming. There are also quiet, older districts where star formation has largely ceased, filled with redder, cooler stars that have burned more slowly. There are star clusters like apartment blocks, where stars were born together from the same cloud, sharing similar ages and compositions. There are regions filled with gas and dust, the raw material from which new stars and planets are made, akin to construction sites where the next generation of structures will rise. These gas and dust regions, called nebulae or molecular clouds, are especially important. In them, gravity pulls denser pockets of gas together, causing them to collapse and heat up until nuclear fusion ignites in their cores. That is how a star is born. Over millions of years, clusters of stars emerge from these clouds, lighting up the surrounding gas in glowing colors you can see in astronomical photographs. When the most massive of those stars reach the end of their lives, they explode as supernova, enriching the surrounding gas with heavier elements like carbon, oxygen, iron, and more. That enriched gas then becomes part of the material for new generations of stars and planets. This cycle of birth, life, and death is ongoing within galaxies. In a sense, galaxies are star factories, continuously transforming simple ingredients like hydrogen and helium into more complex elements that can eventually form planets, oceans, and even living beings. Our own sun is a second or third generation star, and the atoms in your body were forged in stars that lived and died long before the solar system existed. You are literally made of recycled star material, processed through the life cycles of a galaxy. This points to another layer in the city analogy: history. A human city is built over time. It has an old town, historical buildings, newer suburbs, and layers of infrastructure added as generations pass. A galaxy, too, has a history. Many galaxies grew gradually through the slow accumulation of gas and the steady formation of new stars. Others were shaped dramatically by collisions and mergers. Galaxies frequently interact and sometimes collide with one another, especially in crowded clusters. When galaxies collide, their stars don't usually crash into each other directly because the distances between individual stars are so vast. Instead, Their gravitational fields distort one another, pulling out long tidal tails of stars and gas, compressing clouds of gas and triggering bursts of new star formation. Over time, two colliding galaxies may merge into a single, larger galaxy, their stars settling into new orbits. These events are like massive urban redevelopments, reshaping the structure and appearance of the galaxy, city on scales of millions or billions of years. Our own Milky Way contains streams of stars that are the remnants of smaller galaxies it has already absorbed in the past. And about 4 to 5 billion years from now, the Milky Way will likely collide and merge with the Andromeda Galaxy, forming a new, much larger galaxy, sometimes nicknamed Milkomeda. In speculative discussions, if galaxies are cities of stars, then smaller star systems, like our solar system, are like individual households within that city. Each star may have planets, moons, asteroids, and comets orbiting it, just as our Sun does. In a large galaxy, there may be hundreds of billions of planetary systems, each with its own layout, its own potential for complexity. We now know that planets are common. Most stars likely host at least one. So when you imagine a galaxy made of stars, it may also help to imagine a galaxy filled with planets, many times more numerous than the stars themselves. Another subtle but important feature is how galaxies light up the universe, yet leave so much darkness. If you flew through a galaxy, you might expect it to be crowded with stars on all sides, like driving through a city at night with bright lights everywhere. But in reality, space is mostly empty, even within galaxies. The stars are tiny compared to the distances between them. Our nearest stellar neighbor, Proxima Centauri, is about 4.24 light years away. If the Sun were the size of a ping-pong ball, Proxima Centauri would be another ping-pong ball placed hundreds of kilometers away. That's how sparse the population of a galactic city really is. So galaxies are both incredibly full, containing unimaginable numbers of stars, and incredibly empty, where the vast majority of their volume is just space. Temperature and energy vary across these immense structures as well. Some regions are cold, with dense, frigid molecular clouds only a few tens of degrees above absolute zero. Others are blazing hot, such as areas around massive stars or near active galactic nuclei, where temperatures and radiation levels soar. Some galaxies are relatively calm and stable. Others are undergoing furious bursts of star formation or active feeding of their central black holes, making them much more energetic and luminous. The chemical composition of galaxies also evolves with time. Early in the universe, galaxies were composed mostly of hydrogen and helium, the simplest elements formed after the Big Bang. As stars lived and died, they produced heavier elements in their cores and in supernova explosions. Over billions of years, galaxies became progressively enriched with those heavier elements. That's crucial because elements like carbon, nitrogen, oxygen, silicon, and iron are the building blocks for planets, rocks, water, and life as we know it. So a galaxy's chemical history is also part of its character, shaping what kinds of stars and planets can form within it. In all of this, the key idea is that a galaxy is an ecosystem on a staggering scale. Stars form, live, and die. Gas clouds collapse and disperse, star clusters emerge and drift apart, black holes grow, entire galaxies interact, collide, and merge. There is order, regular orbits, stable patterns, and there is chaos, explosions, collisions, tidal distortions. Yet, out of that complexity, we can see patterns, just as you can see a city's skyline and street grid from above. So when we say that galaxies are vast cities of stars, it is not just a metaphor to make you feel awe. It is a concise way to express the idea that a galaxy is a gravitationally bound community of hundreds of billions of stars woven together with gas, dust, dark matter, and a central black hole, all interacting over billions of years. They are the great building blocks of the universe on large scales. If you imagine every star as a home, every cluster as a neighborhood, every spiral arm as a sprawling district, and the dark matter as the invisible foundation, you begin to get a sense of what a galaxy truly is. And in one of those countless star cities, in a quiet spiral arm of a perfectly ordinary galaxy, around a thoroughly average star, there is a small rocky planet where beings have evolved the ability to look outward, study the cosmos, and realize that the glowing band of the Milky Way in their night sky is just a tiny part of a much larger galactic city, a single city among trillions spread across the universe. When we say there are trillions of galaxies in the observable universe, it can sound like an exaggeration, a kind of poetic overstatement. But it isn't. That number is the result of decades of increasingly careful measurement, better telescopes, improved simulations, and a deeper understanding of how galaxies form and evolve. To see how humanity arrived at a number so large, it almost breaks our intuition. We need to trace both the observations and the reasoning behind it. Not very long ago, in cosmic or even human terms, we didn't even know other galaxies existed. For centuries, people looked up at the sky and saw a dome sprinkled with stars that seemed to belong to a single, unified system. The Milky Way, the pale, milky band arching across the sky, was assumed to be the entire universe. The fuzzy smudges that early astronomers saw in their primitive telescopes were catalogued as nebulae, cloudy little patches of light, and their true nature was unknown. By the early 20th century, the big question had crystallized. Were these nebulae just gas clouds within our own galaxy, or were they island universes of what we now call galaxies, far outside the Milky Way? This was at the heart of the famous Great Debate in 1920 between Harlow Shapley and Heber Curtis. It took Edwin Hubble, using the 100-inch Hooker telescope at Mount Wilson, to settle the question by observing a particular kind of star called a Cepheid variable in the Andromeda Nebula. Hubble was able to measure its distance and show that Andromeda was far beyond the limits of the Milky Way. It was an entirely separate galaxy. That discovery alone was a shock. Not one galaxy, but at least two. Soon, more galaxies were identified. As telescopes improved, astronomers realized that the sky, seemingly dotted with stars, also contained countless faint galaxies, each one its own system of billions of stars. The universe, it turned out, wasn't a single city of stars, it was a universe of cities. For much of the 20th century, estimates of how many galaxies there were remained rough. The technology simply wasn't good enough to make out the faintest and most distant ones. It was clear there were many, but many meant millions, then tens of millions, then hundreds of millions, based on what could be seen in photographic plates and early sky surveys. These numbers were always lower bounds. We knew we weren't seeing everything. A major leap came with the launch of the Hubble Space Telescope in 1990. Suddenly, astronomers had a telescope above Earth's atmosphere, free from the blurring and distortion that limits ground-based observatories. Hubble could stare at a single region of space for a very long time, gathering faint light that no human eye and no previous telescope could have detected. That ability led to one of the most transformative images ever taken, the Hubble Deep Field. In the mid-1990s, astronomers pointed Hubble at what appeared to be an utterly unremarkable patch of sky. They deliberately chose a region with no bright stars or no nearby galaxies in the constellation Ursa Major. To an ordinary telescope, or to the naked eye, this region looked empty. Hubble stared at it for about 10 days, taking repeated long exposures, accumulating light from objects billions of light years away. When the composite image was processed and revealed, It changed our understanding of the cosmos. The empty patch turned out to be packed with galaxies, thousands of them, in just that tiny fraction of the sky. Some were spirals like the Milky Way, some were ellipticals, some irregular, some very small and faint, distorted by collisions or still in the process of formation. Each one contained billions of stars. This deep field experiment was later repeated and refined. Astronomers created the Hubble Ultra Deep Field and then an even deeper Hubble E Extreme Deep Field, pushing sensitivity further and capturing even fainter, more distant galaxies. Each time, the conclusion was the same. If a tiny dot of sky the size of a grain of sand held thousands of galaxies, then the entire sky must contain an incredible number of them. To go from these images to a total estimate, astronomers used a simple but powerful idea: extrapolation. First, you carefully count the number of galaxies seen in a deep field image down to a certain brightness limit. You account for the area of sky that image represents, then scale up to cover the full celestial sphere. That gives a first approximation: how many galaxies are visible above a certain brightness in the observable universe. Early estimates based on Hubble data suggested there were about 100 to 200 billion galaxies in the observable universe. Even that number is hard to comprehend. If you tried to count to 100 billion aloud, one number per second, it would take you over 3,000 years without stopping. But astronomers suspected that this number was still too low. Telescopes, even Hubble, have limits. There are galaxies that are so small, so faint, or so distant that their light is barely reaching us, drowned in background noise, or redshifted out of the wavelengths the instrument is best at detecting. In other words, many galaxies are invisible to us, not because they don't exist, but because our tools are still not powerful enough to reveal them. To correct for this unseen population, astronomers began to combine deep field observations with theoretical models and computer simulations of how galaxies form and evolve over cosmic time. One of the most influential studies, published in 2016 by Christopher Consellis and colleagues, took this approach. They examined the distribution of galaxies seen in Hubble's deep images at different distances, and therefore at different ages of the universe, and used that data to build a model of how many galaxies must exist, including those too faint or too small to detect directly. The result of that work was striking. When those missing, undetected galaxies were included, the estimated number of galaxies in the observable universe jumped from a couple hundred billion to on the order of 2 trillion. That's about 10 times more galaxies than earlier counts had suggested. 2 trillion is a number that defies everyday experience. If you wrote the number out fully with commas, it would be 200 billion. If you tried to count each galaxy, saying one number per second, it would take you over 63,000 years. And that's just galaxies, each one an entire system, potentially containing hundreds of billions of stars. To get a sense of how large this is, you can think in steps. Suppose a typical large galaxy contains 100 billion stars. If there were only 100 billion galaxies, and each had 100 billion stars. If you now imagine up to 2 trillion galaxies, and allow that many of them are smaller and dimmer, you still end up with a total star count in the range of 10 to 2 to 10 to stars. That's 10 sextillion to 1 septillion stars. Numbers like these stop feeling like quantities and start feeling more like a different kind of reality. What makes this even more impressive is that these trillions of galaxies are only within the observable universe, the sphere around us from which light has had time to reach us since the Big Bang, about 13.8 billion years ago. Because the universe has been expanding, the most distant observable regions are now about 46 billion light years away. Everything beyond that distance is simply not yet visible to us. The light from those regions has not had enough time to arrive. So when we talk about trillions of galaxies, we are explicitly talking about a limit imposed by the finite speed of light and the age of the universe. The current estimate is trillions of galaxies in the part of the universe we can, in principle, observe. The actual universe might extend much farther, possibly infinitely. If it does, then the true number of galaxies is far beyond even trillions. In that sense, our count is conservative, not an exaggeration, but a lower bound. Of course, science is not frozen. New telescopes continue to refine these estimates. The James Webb Space Telescope, JWST, launched in 2021, has already pushed our reach deeper into the early universe, revealing galaxies that formed just a few 100 million years after the Big Bang. Surprisingly bright and massive galaxies have been detected at these early times, challenging some existing models of galaxy formation. At the same time, some JWST studies suggest that the abundance of the very smallest, faintest galaxies might be somewhat different from what earlier extrapolations assumed. As data accumulates, astronomers may revise the estimated total number of galaxies, maybe down a bit, maybe up. But whether the precise figure ends up at 1 trillion, 2 trillion, or a few 100 billion, the core truth remains: the universe contains an almost unimaginably large number of galaxies. The difference between 500 billion and 2 trillion is a factor of 4, which is important scientifically, but for our intuition, they all reside in the same conceptual territory, a number large enough that no human could ever count or individually catalog them one by one. A crucial piece of this story is how we know we are not double, counting or overestimating. The estimates of galaxy numbers come not just from a single technique, but from the intersection of multiple methods: deep imaging, large-scale sky surveys, models of the galaxy luminosity function, which describes how many galaxies exist at each brightness, and cosmological simulations that track the growth of structure in the universe from the very early stages after the Big Bang. Cosmological simulations start with the initial conditions we infer from measurements of the cosmic microwave background, the afterglow of the Big Bang, and the known laws of physics, including gravity, the behavior of dark matter, and the cooling of gas. They then evolve a virtual universe forward in time, forming dark matter halos, gas clouds, stars, and galaxies. When those simulations are tuned to match the universe we actually observe, its large-scale clustering, the distribution of galaxy sizes and types, and the richness of galaxy clusters, they yield predictions about how many galaxies should exist at different times and at different sizes and luminosities. When you take those theoretical predictions and compare them with what deep surveys like Hubble and JWST actually see, the two lines of evidence can be brought into alignment. The missing faint galaxies that telescopes can't see directly still show up in the simulations as required to explain the patterns we do see. That congruence gives astronomers confidence that the trillions of galaxies estimate is not just a wild guess. It's anchored in both observation and theory. Another way to appreciate these numbers is to think about how they scale with the size of the observable universe. The large-scale structure of the cosmos resembles a cosmic web, matter arranged in filaments and sheets surrounding vast, nearly empty voids. Galaxies live in the nodes and along the filaments of this web, often in groups and clusters bound together by gravity. Trillions of galaxies means that on average, the universe on the largest scales is richly populated, even though any given cubic light year of space is nearly empty. Yet for all that richness, most telescopes only ever show us a tiny fraction at a time. A photograph taken with a typical telescope may show a handful of galaxies or hundreds, depending on its field of view. Even the impressively crowded Hubble Ultra Deep Field is just one minuscule window into the full sphere of the sky. The true abundance of galaxies is something we infer more than directly see. Our instruments give us carefully sampled slices, and science fills in the unseen majority. In daily life, it's easy to forget that the few luminous dots we see above us at night are just the nearest lights of a single galaxy, and that the little fuzzy patch of Andromeda visible from a dark site is only one neighboring galaxy among trillions. It can feel as if space is mostly empty and sparsely populated. The mind-bending truth is that, on the cosmic scale, the universe is teeming with galaxies. If you could somehow step back far enough to see the observable universe all at once, it would be filled with galaxies in every direction, like an endless sea of cities of stars. And each one of those galaxies is not just an object in a catalog, but a possible cradle of complexity. Many of them are likely to host countless planetary systems. Some fraction of those planets will be in the right conditions for liquid water. A smaller fraction may develop life. An even smaller fraction might eventually evolve beings capable of looking out across the universe, as we do, and wondering how many galaxies there are. So when we say trillions of galaxies exist in the observable universe, we are naming a fact with deep implications. It speaks not only to the physical richness of the cosmos, but also to the sheer breadth of possibility. We inhabit one galaxy, orbiting one star on one planet, yet the universe holds billions of galaxies for every person alive on Earth. That awareness can be humbling, even disorienting, but it can also be inspiring. It tells us that reality is far larger, more varied, and more abundant than our instincts alone would ever suggest. When we talk about the observable universe, it's easy to slip into thinking that's just a fancy way of saying the universe. But those are not the same thing. The observable universe is the part we can, even in principle, see or detect. The universe itself may be vastly larger than that, so much larger that all the galaxies we've ever observed could be just a tiny patch of a much grander whole. The key to understanding this lies in two facts. Light takes time to travel, and the universe has a finite age. Light is fast, about 300 kilometers per second, but not infinitely fast. When you look at the moon, you see it as it was about 3 seconds ago, because that's how long light takes to get here. The sun appears as it was about 8 minutes ago. The nearest star beyond the sun, Proxima Centauri, appears as it was about 24 years ago. You are always looking into the past whenever you look out into space. Now add the second fact: the universe is about 8 billion years old. That means there's a maximum distance from which light could have reached us since the Big Bang. Anything farther away than that, in terms of light travel time, hasn't had enough time for its light or any signal to get here. Not because it doesn't exist, but because the cosmic clock started only 8 billion years ago, and the speed of light sets a limit on how far information can travel in that time. You might think that would make the radius of the observable universe 8 billion light years, but it's actually much larger, about 46 billion light years. That sounds contradictory at first, but it makes sense once you remember that the universe is expanding. As space expands, galaxies get farther apart on the largest scales. Light from a very distant galaxy began its journey toward us billions of years ago, when that galaxy was much closer than it is now. While the light was traveling, space itself continued to stretch, carrying the galaxy farther away. By the time the light finally reaches us, that galaxy is not at the distance you would calculate by simply multiplying the travel time by the speed of light. It is much farther. When cosmologists say the radius of the observable universe is about 46 billion light years, they mean If you could pause the expansion right now and measure the current distance to the farthest objects whose light is just arriving, that distance would be around 46 billion light years. Picture yourself at the center of a giant sphere. That sphere is not a solid shell, it's a conceptual boundary called the cosmic horizon, the limit of how far you can, in principle, receive light or signals today. Everything inside that sphere is part of your observable universe. Everything outside is still causally disconnected from you. The light from those regions has simply not had enough time to arrive. This might sound as if we are at some special central point in the universe, but that's not the right interpretation. Every observer, wherever they are in the universe, has their own observable universe, a sphere centered on them. A galaxy billions of light years away has its own horizon, its own observable region that overlaps with ours only partially. There is no single center of the universe. There are countless centers, one for every observer, each with its own observable bubble. So the observable universe is not the whole universe. It is just the part of the universe that has had time to send us information. Think of it like standing in a foggy field at night with a lantern. You can see only so far in every direction, limited not by distance itself, but by the way light is absorbed in the fog. Beyond that, the field continues, but you have no direct view of it. Our situation is similar, except that our fog is the combination of the finite age of the universe and the finite speed of light. There is another important layer here. The phrase observable universe already assumes ideal conditions, perfect instruments, infinite patience, and the ability to detect any form of signal. In practice, we're more limited. For example, the universe was not always transparent. In its very early history, before about 380 years after the Big Bang, it was hot and dense enough that atoms couldn't form. Electrons and protons were flying free, scattering photons constantly. Light couldn't travel very far without being absorbed and re-emitted, so the universe was opaque, like the inside of a star. When the universe cooled enough for electrons and protons to combine into neutral atoms, mostly hydrogen, it became transparent to radiation. The photons that were bouncing around then have been traveling through space ever since, gradually stretched to longer wavelengths by the expansion of the universe. We detect that ancient light today as the cosmic microwave background, CMB, a faint glow in microwave wavelengths that fills the sky. The CMB comes from a surface of last scattering, a kind of photosphere representing how the universe looked when it first became transparent. Beyond that surface of last scattering, we can't see using light at all, not because nothing is there, but because the universe was opaque at earlier times. We can infer what happened earlier from theory and from subtle patterns in the CMB, but we can't take a direct picture. That pushes an effective limit a bit closer in than the absolute horizon defined by the age of the universe. Even given these complications, the core idea stands. Our ability to observe is always bounded both by physics and by time. No matter how good our telescopes become, we will never see beyond the cosmic horizon any more than we can see beyond the current edge of the fog in that field. This means that when we count galaxies and say there are on the order of trillions in the observable universe, we are really only talking about the contents of our observable bubble, not the full extent of cosmic reality. What lies beyond that horizon? This is where observation starts to give way to inference. From what we can see, the universe appears remarkably uniform on very large scales. The distribution of galaxies and the patterns in the cosmic microwave background look statistically the same in every direction once you average over hundreds of millions of light years. This isotropy, sameness in all directions, and homogeneity, sameness in all locations, on large scales suggests that the part of the universe we can't see is probably similar, at least nearby beyond The horizon, our observable patch, does not seem special or different. It looks like a representative sample. We also measure the geometry of space using the CMB and the distribution of galaxies. So far, all the data are consistent with the universe being very close to spatially flat on large scales. A flat universe, in the sense of general relativity, is one in which parallel lines stay parallel, and the rules of Euclidean geometry apply on cosmic distances. If the universe is flat and matter and energy are distributed more or less uniformly, then it naturally follows that the universe is either infinitely large or so much larger than the observable region that any curvature is too small for us to detect. Cosmic inflation, a leading theory describing the universe's first tiny fraction of a second, reinforces that picture. Inflation proposes that space itself underwent an incredibly rapid, exponential expansion just after the Big Bang, smoothing and stretching any initial irregularities. If inflation occurred as we think, it would have blown up a small, causally connected region into something much, much larger than the part we can see today. Our observable universe would then be just one little patch on a much larger inflated space. Some inflation models even suggest the existence of a multiverse, a vast collection of regions where inflation ends at different times, each forming its own bubble universe with potentially different physical conditions. That idea is still speculative and lies beyond what we can test directly, but it underscores the point. What we can observe may be just one region of a much grander cosmic structure. Even without venturing into multiverse territory, there's a simpler, solid conclusion. Nothing in our data suggests that space stops at the edge of what we can see. There is no sign of a literal border, wall, or edge beyond the observable universe. The edge is not a physical boundary in space. It is a boundary in time and causality. The universe very likely continues beyond it, as smoothly and naturally as a landscape continues beyond the horizon of the Earth. This has a striking implication for the idea of trillions of galaxies. When we say there may be up to about 2 trillion galaxies in the observable universe, we're describing just the content of our observational bubble. If the universe beyond is similar, there would be additional galaxies outside our reach, perhaps vastly more. If the universe is infinite, then the number of galaxies is effectively unbounded, even though only a finite portion is ever accessible to us. There is also the fact that our observable universe is shrinking in a different sense, due to the accelerated expansion of the universe driven by dark energy. Distant galaxies are receding from us faster and faster. Some of them are already crossing what's called the cosmic event horizon, a boundary beyond which even light emitted now will never reach us in the future because space between us and them is expanding too quickly. Over extremely long timescales, more and more of the universe will slip beyond causal contact, and the observable portion, in terms of what we can communicate with or receive new information from, will effectively get smaller. All of this highlights an important philosophical shift that modern cosmology brings. Our perspective is deeply limited. For most of human history, we thought the universe meant our local environment, Earth, the sun, a few wandering lights in the sky. Then we discovered the solar system is just one system among billions in a galaxy. Then we found that the Milky Way is just one galaxy among billions or trillions in the observable universe. Now we realize that the observable universe itself may be just a tiny part of an even larger, perhaps infinite, reality. The observable universe is, in a sense, our cosmic island, the volume of space we can interact with. It defines the playground for our observations and experiments, but the ocean beyond that island, though forever hidden from direct view, is almost certainly there. Our best theories and measurements suggest that the universe extends far past what we can see, filled with regions we will never reach, populated by galaxies whose light will never grace our telescopes. So when we look at deep images full of galaxies and say, "This is the universe," we should remember we're actually looking at one small, though magnificent, sample. The mind-bending truth is not just that there are trillions of galaxies. It's that those trillions are very likely only the contents of our observable patch, one finite window into a cosmos that may be far vaster than we can ever directly know. When you walk outside on a clear night and look up, it can feel as though you're seeing the universe as it is right now, a live view like a window. But that's not what's really happening. You are not looking at space as it is, you're looking at space as it was. Every point of light above you is a message from the past, and the farther away it is, the older that message becomes. The reason is simple but profound. Light takes time to travel. Light is incredibly fast, about 300 kilometers per second, but it is not instantaneous. That means whenever you see something by its light, you're seeing it not as it is at this exact moment, but as it was when that light first left it and began its journey toward you. You already experience this on human scales, but the delay is too tiny to notice. When someone flips a light switch across the room, the light reaches you in a tiny fraction of a second. For all practical purposes, it seems immediate, but on cosmic scales, where distances are measured not in kilometers but in light years, that delay becomes huge. A light year is the distance light travels in 1 year, about 9.46 trillion kilometers. When we say a star is 10 light years away, we mean that its light takes 10 years to reach us. Look at that star tonight, and you are seeing it as it was 10 years ago. If something dramatic happened there yesterday, if the star exploded, for instance, you wouldn't know for 10 more years. The universe doesn't send live broadcasts, it sends delayed recordings. Consider our own neighborhood in space. The moon is about 1.3 light seconds away. When you see it, you're seeing it as it was a little over a second ago. That doesn't change much for us emotionally, but it's already a measurable delay. The sun is about 8 light minutes away. If the sun were to magically disappear right now, Earth would continue orbiting as if nothing had happened for 8 minutes, and we would still see the sun shining in the sky for those 8 minutes. Our entire sense of now, when we look at the sun, is 8 minutes out of date. Move to the nearest star beyond the sun, Proxima Centauri 4.24 light years away. The light hitting your eyes from that star tonight began its journey when you were 4 years younger. You can think of the sky as a kind of time map. Nearby objects are recent, and the farther your gaze goes, the older the universe you're observing. When you shift from individual stars to galaxies, the time travel effect becomes staggering. The Andromeda Galaxy, the nearest large galaxy to the Milky Way, is about 2.5 million light years away. The light you see from Andromeda tonight began its journey when early humans were just starting to use stone tools. Every time you see that faint smudge in the sky, you are literally looking at a message from the time of our distant ancestors. Beyond that, some galaxies are so far away that their light has been traveling for billions of years. Look at a galaxy whose light has a 5 billion year journey behind it, and you're seeing the universe as it was before our sun and earth even existed. Find one whose light has been en route for 10 billion years, and you're looking at an infant universe, only a few billion years old. Astronomers use this built-in delay to their advantage. Telescopes are, in a very real sense, time machines. They cannot move us through time, but they allow us to see different eras of cosmic history simply by looking at more and more distant objects. Nearby galaxies show us the universe as it is now, or at least in the recent cosmic past. Slightly more distant galaxies show us what galaxies were like billions of years ago. Extremely distant, very faint galaxies reveal what the universe looked like not long after the Big Bang. This is why deep field images are so powerful. When telescopes like Hubble or the James Webb Space Telescope stare at a tiny, seemingly empty patch of sky for many hours or days, they gather the faintest trickle of light from the most distant galaxies. Some of that light set out more than 13 billion years ago. When we detect it, we're seeing those galaxies as they existed less than a billion years after the universe began. There is a term astronomers use called look-back time. If a galaxy's light has been traveling for 3 billion years, its look-back time is 3 billion years. We are looking back 3 billion years into the past when we observe it. As you construct a catalog of galaxies at different look-back times, you build a kind of photo album of the universe's life story, how galaxies were structured long ago, how frequently stars were forming, what kinds of stars existed, and how things changed over billions of years. Another concept that comes into play is redshift. As light travels through the expanding universe, the space between us and the distant object stretches. That stretching increases the wavelength of the light, shifting it toward the redder end of the spectrum. The farther away a galaxy is, and the longer its light has been traveling, the more its light is redshifted. Astronomers use this redshift as a kind of time stamp, measure how stretched the light is, and you can infer how long it has been traveling, which tells you how far back in time you're looking. At extremely high redshifts, you begin to approach the earliest observable epochs. Eventually, you reach a point where you no longer see ordinary galaxies at all, but instead you encounter the afterglow of the Big Bang itself, the cosmic microwave background. This faint radiation comes from when the universe was only about 380 years old. Before that time, the universe was hot and opaque, filled with a plasma of particles that scattered light constantly. Light could not travel freely. Once the universe cooled enough for atoms to form, space became transparent, and that light was released to travel almost unimpeded for billions of years. When we detect the cosmic microwave background today, we are seeing through radio and microwave telescopes the universe as it was when it transitioned from opaque to transparent. That is our oldest direct picture of the cosmos. In that sense, the night sky is not just a map of where things are, it is a layered history of when things were. Closer stars are chapters from the recent past. Distant galaxies are chapters from the early universe. The cosmic microwave background is the opening page of the story, as far back as light will let us see directly. It's important to note that this idea of looking back in time doesn't mean we are seeing objects moving away in some kind of film loop. When you look at a distant galaxy and see it as it was 10 billion years ago, that doesn't mean you can then watch it age in real time. The light from its later years will arrive in the future, spread across billions of years. For humans who live at most a century, cosmic evolution is far too slow to watch unfold. Instead, astronomers compare many galaxies at different distances, like snapshots of different ages, and piece together a general timeline. This time, traveling view has revealed that the universe was a very different place in its youth. Early galaxies were often smaller, more chaotic, and more actively forming new stars. Over time, many merged, grew, and settled into the grand spirals and ellipticals we see today. Star formation peaked roughly 10 billion years ago and has declined since. Heavy elements, forged in stars and supernova, were scarce at first, and became more abundant as more generations of stars lived and died. All of this is inferred by looking at galaxies at different look-back times and recognizing patterns. The fact that we see the past when we look outward also changes how we think about now on a cosmic scale. There is no universal cosmic present that we can access by looking across the sky. Each direction and distance corresponds to a different slice of the universe's history. When you look at a star in our galaxy, you might be seeing back a few hundred or thousand years. When you look at a far, off galaxy through a telescope, you might be seeing back billions of years. These nows are all mixed together in our view. Our mental image of the universe at this moment is stitched from light of many different ages. And yet, despite this patchwork of times, we can use physics, relativity, cosmology, and careful measurement to reconstruct what the universe as a whole is probably like right now in our frame. We can estimate how much those distant galaxies have continued to evolve since the light we see left them. This is a bit like seeing an old photograph of a person and knowing how people age, imagining what they might look like today. We never see the actual present state of most of the universe, but we can infer it. It's not only light that carries these time-delayed messages. Gravitational waves, ripples in spacetime caused by massive events like black hole mergers, also travel at the speed of light. When detectors like LIGO pick up a gravitational wave, they are also hearing an event that happened long ago and far away. Neutrinos, nearly massless particles that barely interact with matter, can also arrive from distant cataclysms, bringing their own faint, time-lagged signals. All of these messengers obey the same rule. Travel takes time, and so every cosmic signal is a relic of the past. Realizing that looking into space is looking back in time has a subtle but powerful consequence for how we think about our place in the universe. We are not just tiny in space, we are also tiny in time. Our entire recorded history is a blink compared to the age of the universe. Yet, from our short-lived vantage point, we've managed to read billions of years of cosmic history simply by decoding the delayed light around us. When you gaze up and see a star, you are receiving its ancient story. When astronomers point giant telescopes at a distant galaxy and split its light into a spectrum, they are reading clues about its composition, its motion, its age, and the era of the universe it comes from. In this way, the cosmos becomes not just a collection of objects scattered in space, but a narrative unfolding in time, a narrative we can partially reconstruct because light needs time to cross emptiness, so the night sky is not just overhead, it is also behind us, stretching back through deep time. Every faint glow is a record of what was. To look farther is to look earlier. And that simple fact, born from the finite speed of light, turns the universe itself into a vast natural time machine, one that lets us, on our small planet, piece together the story of how everything came to be. When people first hear that there are trillions of galaxies, each with billions of stars, something almost instinctive often happens, a feeling of shrinking. Our planet becomes a speck, our lives a flicker. The thought forms almost on its own, if the universe is that big, then I must be nothing, what I do can't possibly matter. But that feeling, powerful as it is, rests on a hidden assumption. That size determines value. The larger something is, the more it matters. The smaller, the less it counts. Once you see that assumption, you can start to question it, because there is no good reason to believe that physical scale and meaning move together. Imagine a violin. It is small compared to a concert hall, tiny compared to a city, invisible on the scale of the Earth, and absolutely negligible compared to the galaxy. Yet music played on that violin can make someone weep, remember a lost loved one, or feel hope after despair. The physical size of the instrument has nothing to do with the depth of the experience it creates, or think of a single conversation between two people. To the planets and stars, it's nothing, but if in that conversation one person apologizes, or forgives, or confides for the first time, it can alter the course of a life. The volume of space that moment occupies is microscopic. Its emotional and moral weight is enormous. Meaning lives in a different dimension than size. It exists in experience, in relationship, in consciousness. A universe a trillion times smaller than ours with no conscious beings in it would be, in one sense, infinitely less meaningful than our enormous universe with at least one tiny pocket where beings can think, feel, love, fear, and wonder. That is the first key point. Significance is not measured in meters or light years. Now consider what you are. Physically, you are made of atoms forged in stars. Hydrogen that has existed since shortly after the Big Bang sits side by side with heavier elements carbon, oxygen, nitrogen, iron created in the cores of massive stars and scattered in supernova explosions. For billions of years, the universe existed with no life, just matter and energy rearranging under physical laws. Eventually, in at least one place, some of that matter organized itself into molecules that could copy themselves, adapt, and evolve. Those early life forms changed, split, and diversified over unimaginable stretches of time. Nervous systems appeared. Brains formed, memory, awareness, and emotion emerged. You are the current and point of that chain, or more precisely, one end among many. Your brain is a network of billions of neurons, each connected to thousands of others, forming patterns of activity that somehow support thoughts, feelings, language, imagination, and a sense of self. This intricate structure, made of matter born in stars, has gained the ability to ask questions about its own origin and about the universe it inhabits. That alone is extraordinary. There are entire clusters of galaxies where, for all we know, nothing like this has ever happened. Most of the matter in the universe, dark matter, dark energy, hydrogen clouds, barren rocks, probably never participates in anything like consciousness. Trillions of stars will shine and die without ever being seen or known by anyone, yet here, on one planet orbiting one star in one galaxy, matter has become aware. The universe, through you and others like you, knows that it exists. It understands some of its own laws. It can reflect on its own immensity. This is not poetic exaggeration. It is a straightforward consequence of what we are, arrangements of cosmic material capable of modeling the cosmos. When people say, we're insignificant because we're so small, they are comparing the wrong things. The right comparison is not between the size of a human and the size of the universe. The right comparison is between a universe with no conscious beings and a universe with at least one. The second universe contains something the first absolutely lacks: the possibility of meaning, value, joy, sorrow, curiosity, ethics, and purpose. Without minds, the universe just is. It has structure, certainly. It has beauty, if by beauty we simply mean elegant mathematical patterns. But there is no one there to see a sunset, to be moved by the shape of a nebula, to be fascinated by the laws of physics, or to suffer injustice. With minds, all of that becomes real. The very idea that anything could matter is inseparable from the existence of beings who can care. In that sense, consciousness does not need the universe's permission to confer importance. The moment there is someone who can feel pain, the difference between harm and care becomes meaningful. The moment there is someone who can love, that love matters to them, and often to others regardless of whether any galaxy notices. The universe does not keep score, it doesn't need to. For the beings inside it, the score is written directly in experience. Now add a sobering detail: as far as we currently know, we are alone. We have no confirmed evidence of life elsewhere, let alone intelligent life. We have scanned parts of the sky for artificial signals. We have found thousands of exoplanets. We have looked for signs of civilizations using massive amounts of energy. So far, nothing has spoken back. This may change. Perhaps one day we will detect unmistakable evidence of other minds among the stars. That would be one of the greatest discoveries in history, and it would expand, not reduce, the significance of consciousness in the universe. But until that happens, we have to work with the facts we have. Life is common on Earth, but unknown elsewhere, intelligent, Technological life is known only here. This doesn't prove we are unique in the cosmos, but it strongly suggests that consciousness is at least rare in our observable region. If you stumbled upon a vast desert and found a single oasis with water and plants and animals, would you call it insignificant because the desert is big? Or would you recognize that, precisely because the desert is vast and mostly barren, the oasis is precious? Earth is that oasis, as far as our evidence reaches, a blue, living world in a universe where most places are frozen, blazing, or empty. If conscious life exists nowhere else, then this planet carries the entire known burden of awareness. If conscious life does exist elsewhere, our planet is still the only one we can care for directly right now. Either way, what happens here is not trivial. Think of a fragile library in a world of stone. If there were only one place where stories, knowledge, and memories were written down, its survival would matter enormously, not to the stones, but to anyone who can read. Our civilization, and indeed all life on Earth, is like that library of experience and potential in a universe predominantly made of unthinking matter. That brings us to responsibility. The cosmic perspective does not just produce humility, it also produces a sense of duty. We are small, yes, we are not the center, but we are also powerful in our local sphere. We can alter climates, extinguish species, create technologies that change the face of the planet. We can wage wars that threaten our own survival. We can also choose to protect ecosystems, pursue knowledge, and alleviate suffering. If consciousness is rare and fragile, then protecting it becomes a meaningful project. Whether you frame that in scientific terms, spiritual terms, or ethical terms, the conclusion is similar. Our choices matter a great deal to the beings who exist now, and they may matter to whether beings exist at all in the far future. Someone might still object, but in a few billion years the sun will die, eventually everything will end. Doesn't that erase the meaning of everything we do? That objection assumes that meaning requires permanence, that for something to matter, it has to last forever. But we don't apply that standard in our actual lives. A conversation that lasts an hour can change a person forever. A piece of music that lasts 5 minutes can comfort someone in deep grief. A life that lasts 80 years can be profoundly worthwhile, even though it is finite. The fact that something ends does not retroactively delete its value. Joy that is felt, love that is given, pain that is eased, these are real in the moments they occur. They matter then, and often long after, in the memories and consequences they leave. The universe's final state, whatever it may be, does not reach back and cancel out the reality of what happens now. Meaning is not waiting at the end of time to pass judgment. It is constructed and lived in the present. The immensity of the cosmos can actually deepen this sense of lived meaning. When you know that you are a fleeting arrangement of stardust in a universe that will go on without you, your choices can feel more urgent, not less. If your time is brief and unrepeatable, then how you spend it matters more, not less. Each act of kindness, each moment of genuine connection, each attempt to understand the world becomes a deliberate use of a limited, precious resource. It can also connect you to something larger in a healthy way. You are not the universe's center, but you are a tiny part of its unfolding story. The atoms in your body have traveled through stars and interstellar space. They have been parts of other forms before they were you. After you die, they will go on to be parts of other systems. For a short time, you are a configuration of the universe that can look back at itself. Whether or not that feels like cosmic purpose to you, it is at least a remarkable opportunity. You may find meaning in relationships, in creative work, in learning, in service, in contemplation. None of those is invalidated by the distance to the nearest galaxy cluster. The Andromeda Galaxy will still be there whether you treat people well or badly, but the people around you will not. Their experiences and yours are where the stakes are. If someday we do encounter other intelligent beings, the picture will get even richer. We will no longer be just the universe becoming aware of itself in one place, but part of a community of awareness spread across space. Until then, we carry that awareness alone as far as we know. The weight of that role is not something to despair over, it is something to rise to. So the existence of trillions of galaxies does not make you meaningless, it makes your existence and the existence of every conscious being all the more striking. Against a backdrop of vast, mostly indifferent processes, there are a few small places where kindness can happen, where understanding can grow, where beauty can be perceived, where courage can be shown. You are in one of those places, you help create it. The universe is large, you are small. Both of those can be true, and it can still be true that what you do, how you live, and how you treat others truly matters. Learning that we live in a universe with trillions of galaxies is not just an interesting scientific fact, it has emotional and ethical consequences. It challenges how we see ourselves, each other, and our planet. Out of this realization naturally arise three intertwined attitudes: humility, wonder, and responsibility. Humility comes first, and in a sense, it is forced on us by the sheer scale of what we've discovered. For most of human history, we imagined ourselves at the center of things. The sun seemed to circle the earth. The stars appeared as small lights placed in a sky made for us. Myths and early cosmologies often positioned humanity as the main point of existence. Modern astronomy has dismantled that picture step by step. Earth is not the center of the solar system, the sun is. The sun is not at the center of the galaxy. It is one of hundreds of billions of stars orbiting a black hole in an ordinary spiral arm. The Milky Way itself is not special. It is one galaxy among trillions in the observable universe. Even the observable universe may be just a tiny patch of a much larger whole. This is a profound demotion of our physical status. It tells us clearly, we are not the stage on which the universe was built to perform. We occupy no privileged location, our galaxy is not uniquely favored, our star is not exceptional. Properly accepted, this knowledge dissolves a certain kind of arrogance. It makes it hard to insist that our particular group, nation, religion, or era is the absolute center of reality. The cosmic perspective shows that many of the boundaries we obsess over, borders on maps, ideological divisions, social hierarchies, are microscopic when viewed against billions of years and billions of light years. That recognition can soften dogmatism. It invites us to take our beliefs seriously, but not to mistake them for the measure of the universe. Yet humility alone is not the whole response. Alongside it, and just as naturally, comes wonder. If we are not the center, then what are we? We are a small, temporary manifestation of something far larger and older. A universe that has been evolving for nearly 14 billion years. The atoms in your body were forged in stars that lived and died long before Earth existed. The calcium in your bones, the iron in your blood, the oxygen you breathe, the carbon forming your cells, all of these elements were created in stellar furnaces and supernova explosions scattered across the galaxy. For billions of years, these elements drifted in cold space, part of gas clouds and dust. Eventually, gravity pulled them together into a new star and planet. On that planet, through processes we still don't fully understand, some of that matter organized into living cells. Those cells evolved into organisms, and among them, one species emerged with brains capable of memory, symbol, art, science, and self-reflection. That is what you are. A moment in which the universe has become aware of itself. You are made of the same stuff as distant galaxies, but arranged in such a way that you can think about galaxies, feel awe at their beauty, and ask where you belong among them. Wonder is the natural response to this realization. It is not naive, it is a form of honesty about how strange and improbable our situation is. Wonder is what opens us to beauty instead of despair when we contemplate our smallness. You can look at the night sky and feel crushed by scale, or you can feel amazed that a being so small can comprehend so much. You can hear that the sun is one average star among countless others and feel pointless, or you can feel gratitude that, against all odds, you happen to arise around one such star with the ability to know it. Humility tells us we are not the center of the story. Wonder tells us that the story is still astonishing and that our part in it is anything but trivial. From these two, humility and wonder, follows responsibility. If Earth were one of millions of known life-bearing planets, teeming in a crowded galactic neighborhood, our choices might still matter, but the stakes would feel different. If we ruined our world, there would at least be others where life and perhaps intelligence had also risen. But as far as we currently know, that is not the case. We have found thousands of planets around other stars, but we have not yet found a single confirmed sign of life elsewhere, let alone intelligent life. This doesn't prove we are alone, but it strongly suggests that life, and especially conscious life, is rare. For now, our planet is the only known cradle of awareness in a universe otherwise silent. Seen this way, Earth is not just our home. It is a unique, fragile oasis in a vast desert of space. Its thin atmosphere, its liquid water, its stable climate, its web of interconnected species, all of this is astonishingly delicate. We now know that our actions can damage this system on a planetary scale, changing the climate, acidifying the oceans, destroying habitats, wiping out species, and even threatening our own long-term survival. If conscious beings are rare, then protecting the only known community of such beings becomes a moral project of cosmic importance. The responsibility is twofold. First, we have a responsibility to each other. In a universe that will not step in to rescue us from our own mistakes, how we treat one another is all the more crucial. The cosmos is indifferent, but we don't have to be. Our ethics are decisions about justice, compassion, cooperation, and conflict shape the only part of the universe where suffering and joy are known to exist. That makes them deeply consequential. Second, we have a responsibility to the larger web of life on Earth. Our species is powerful enough to act as a geological force, reshaping entire ecosystems. With that power comes the obligation to use it wisely. We can choose to be caretakers rather than mere exploiters. Protecting biodiversity, preserving habitats, reducing our destructive impact, these are not just environmental policies, they are ways of honoring the rarity of living worlds in a cosmos dominated by lifeless rock and vacuum. Humility without responsibility can become passivity. We're tiny, nothing we do matters. Wonder without responsibility can become mere entertainment. The universe is beautiful, let me just watch and feel things. Responsibility ties them together and turns insight into action. It says, precisely because we are small, and because life is rare, the patch of reality we can influence deserves our care. We may never travel to other galaxies, most of us will never leave Earth, but every one of us participates in small ways in shaping this one world. Our choices about how we live, what we value, and how we treat other people and other species ripple outward. Against the background of trillions of galaxies, those ripples may seem tiny. For the beings touched by them, they are everything. Learning about the vastness of the universe does not require us to diminish ourselves. It invites us to see ourselves clearly as finite, fallible creatures in a boundless cosmos, yet capable of understanding, appreciation, and care. From that clarity arises a quiet, sturdy stance. Walk humbly, look up in wonder, and act with a sense of responsibility for this planet, for each other, and for the fragile, extraordinary phenomena of life itself.